Well, we have been covering derivatives in, I guess, to exhaustion, meaning that we are fully capable of taking the derivative of just about any function that we can get our hands on. At least that's our goal by the end of this chapter, to have done that. What we're going to do now is throw in it here at the end of Chapter 2, one example or application where derivatives can be useful. In particular, thinking of derivatives as rates of change. I just want to refresh our memory because of the fact that it's been a while since we've talked about this, but remember that when, say for example, the independent variable is time, or we usually denote that by t, okay, then, for example, and the dependent variable let's say, for example, is position. Let's say we have s of t, okay, then ds dt represents what I call velocity, right? We've talked about thinking of the derivative as this rate of change. What velocity then represents is the change in position over time, or rate of change with respect to time. This term speed is also sometimes used. Generally, what speed represents is the absolute value of the velocity. Right? Velocity has a direction to it, a positive or negative value in general. So you could have something traveling at 500 miles per hour or negative 500 miles per hour. Depending on what direction that variable represented, then you have a positive direction and negative direction to it. Speed, we generally just mean the absolute value of whatever the velocity is. So what your speed is at any given point is the speed you're traveling in the direction you're currently moving. Okay? What would the second derivative with respect to time represent? It's acceleration. In fact, if I were to call that v, then the second derivative with respect to time is like the derivative of the first derivative, which is the same thing as dv dt, which is how fast your velocity is changing. Meaning, are you increasing speed? Are you decreasing speed, which the term we use for that is acceleration. There's actually a third derivative. I don't think this book talks about it. I just throw it in here because I like the name for it. The third derivative of position with respect to time is called the jerk. Because a change in acceleration, a sudden change in acceleration, what effect does that have on you? You throw the pedal down to the metal, you jerk, right? So that is that change in acceleration, okay? So a constant acceleration means you're increasing speed at a constant rate. So I started going 0 miles per hour. If I end up going 60 miles per hour after 5 seconds, then I increased 12 miles per hour every second, right? That's a constant acceleration. But if you have a sudden change or you have an increase in acceleration, that means not only you're speeding up, but the rate at which you're speeding up is speeding up, which causes, again, that sensation of a jerk, but that's the name for it. Okay? So anyway, it's important to remember that that's what we think of when we think of derivatives in a physical context as rates of change. Another way to think of rates of change is just change with respect to one variable over another variable. If, say, x has 1 unit, okay, think length or volume or whatever, and y has another unit, okay, then dy dx will have the units of y per units of x. So, for example, if your dependent variable, say your x was time, like minutes, and your y was gallons, then the derivative is gallons per minute. It's the rate at which something is happening. So that's important to consider when we start talking about relative rates of change or related rates. What we're going to do is we're going to look at the relationship between two variables and then identify, well, what's the relationship between how fast they change? If we know one variable depends on another, like the area of a circle depends on the radius of the circle, okay, then how fast will the area change when the radius is changing? So imagine the radius of a circle is changing at a certain rate. How fast is the area changing? Like radius would change in like unit measures of, I don't know, inches per second. Okay? How fast is the area changing? Square inches per second. How fast are those related to each other? And it depends on the original relationship of the two. So that's what we're going to be talking about when we talk about related rates. Okay? All right, so let me start with an example. Consider, and we're going to just see how well I can draw using this little tablet here. So if this gets ugly, we may have to go call up the textbook on the web page that I've got where I can do that and just look at the picture. But I'll do the best I can. Consider a cone funnel. And I mean like a right cone, circular, like this, right? That's filled with water. Okay, and so it's dripping out down here. Let's say the height of the water is h, and the radius at the top of the water is r. Okay, can anybody here tell me what the volume of water is for a right cone, right circular cone? You remember from your geometry? Not a 1? Collective intelligence in here should be at least enough to get some idea. Ooh, you're close. There's a fraction involved. It's a third, yes. 1/3. And there's a pi involved because of the circle, right? So pi. There's got to be an r in it. So in fact, it has to do with the area of the base, which happens to be pi r squared, but also dependent on the height. And it's actually proportional to the height, so it's just times h. There's your volume. We got there. We got there.
You got there.
Y'all threw some fractions at me. You're close. You knew there was a pi. Come on, we eventually got there. By the way, we will derive and prove that that is in fact the volume before the end of your calculus career here at Wayland. We will know why that's true, not just that it is true. All right, so let's differentiate both sides with respect to t. Now, what is t? T is somewhere hiding in this problem because this funnel has a hole at the bottom, so the water's trickling out, right? So what is changing? Over time, everything's changing, right? Volume would be changing because you got water leaving. Would your radius be changing? As the water goes down, you might be down here, right? Which means your R is now smaller. Your H is also smaller, which means your volume is smaller. So V, R, and H all depend on T. However, pi does not. Pi does not change ever. So if I say take the derivative of both sides with respect to T of V and take the derivative with respect to T of pi R squared H, this is an implicit differentiation problem just like we've been doing, except now we've got several variables that all depend on T. Which means that every time you take the derivative of a variable that depends on t, take the derivative as if it was with respect to that variable, and then multiply by the derivative of that variable with respect to t. Like we did with the y, whenever you took the derivative of the negative y up there, you end up with a -1, and then times dy dx, right? So I'm suggesting when you take the derivative of v, you get 1. times dv dt, or just dv dt. Okay, what about the right-hand side? Well, first of all, I lost a third, and I don't know where it went, so we'll stick it back in there. Sorry.
What does that say? Diff both sides WRP?
Yeah. Did you not hear what I said when I wrote that? Ah, yeah. I'm using abbreviations that I should probably put down at least once in your note. With respect to, I will use that one a lot.
I thought that was.
Yeah, it looks like gibberish if you have no idea what I'm talking about. Worked to. So diff stands for what? Differentiate with both sides. WRT is with respect to. You'll see me use that quite a bit, so get the hang of it. You'll see other math professors use it too. It's kind of a conventional doohickey. All right, now 1/3 pi is a constant, so it stays out front. Now let's take the derivative of this. Now r depends on t, h depends on t, so this is a product of two functions that depends on t, which means I have to use the product rule, right? What's the product rule? First times the derivative second. Okay, what's the derivative of h with respect to t? 1 times d dt. Yes, dh dt. Okay, if you want to stick that 1 in there just so you know that it's there too, by all means do that. But eventually it's going to go away. Plus the second. And what's the derivative of r squared? 2r times dt. That's the chain rule, right? That's always the chain rule. That's the implicit differentiation technique that we use. Okay? Does that make sense? Can you do that? When you take the derivative of a variable other than the one you're taking with respect to, you do it just like you're doing that variable and then times the derivative after it. Okay? So with a little bit of simplifying, we get dv dt is equal to 1/3 pi times r squared dh dt plus 2 rh dr dt. Okay, so this equation shows how the rate of change of volume depends on the rate of change of h and r. This equation shows how the rate of change of volume depends on the rate of change of h and r. Okay? So what these types of questions will look like is you will be asked to find the rate of change for a particular variable, and you will be given enough information about what the other variables are and the other rates are at that time. So for example, I might have said, okay, when the radius reaches 2 and the height reaches 2, and we know that the height is changing at this rate and the radius is changing at this rate, how fast is the volume changing? With all of that, I told you enough information to fill in the right-hand side and calculate it. Okay? So in general, what these problems will look like is you'll be given a scenario. You have to set up your equation up here. You'll have to identify some givens, okay, which would be things like r dh dt, r h dr dt, and then you'll have to answer a question. Okay? So then you'll have to find something. Let's do one simple where I just give you the equation. So for example, let's say the problem is let y equals x squared plus 3. I want you to find dy dt when x equals 1, given that dx dt is 2 when x is 1. All right? So notice, what is this derivative with respect to in the question? Yeah, the top variable is what you're taking the derivative of, right? So we're taking the derivative of y. With respect to is the bottom variable, t. So dy dt means the derivative of y with respect to t. Now notice, what variables do we have in this problem? Y and x, which means in order to find dy dt, we're going to assume y and x both depend on t. That's so that we remember to use the chain rule whenever we take these derivatives, okay? So let's do d dt of y and d dt of x squared plus 3. So we first differentiate both sides, and here I go again, with respect to t. So what is the derivative of y with respect to t? The derivative of y is 1 times dy dt. And I'll go ahead and write the 1 in there just so you see it. What is the derivative of x squared with respect to t? Dx dt, exactly. And the derivative of 3? 0, so done. So that says dy dt is equal to 2x dx dt. Okay? Now we're asked to find dy dt, but we're given that x is equal to 1, right? And we're also given that whenever x is equal to 1, dx dt is equal to 2. So dx dt equals 2, which means dy dt is 2 times 1 times 2, or 4. Okay? So y is changing at 4 units per unit of time. So I'm going to start emphasizing this. Here's the equation, right? Here was the given information. And then we were asked to find this. So you got to have an equation, you got to be given some information, then you got to know what you're going to try to find. Okay? All right, let's do some actual problem solving. Let's set up some that have some physical context. All right? Well, I'm going to, just because I don't want to write down the full problem, and I didn't type up anything for you to have, I'm going to ask you to go ahead and open up in your textbook. You've got it. If not, look on with somebody next to you. In section 2.7, we're going to go through the examples that are in this section of the text. And we're going to go as far as we can before we run out of time, but a few examples will get you started, and you can read the rest as you need as you're working on these problems. It's on page 141 is the first one I want to do. This example is called ripples. I can write ripples on a pond. So the idea is you toss a stone into a pond, and what happens is the waves begin to ripple out from the center, and they expand over time. And so on, right? So you got a radius of that outer ring. The text says that a pebble is dropped into a calm pond, causing ripples in the form of concentric circles, which is what I've drawn for you here. We know that the outer radius, the outer ripple, I guess, it has a radius that is increasing at a constant rate of 1 foot per second. Outer ripple, changing at 1 foot per second. When you see per, you need to start from this point forward thinking derivative, because that is a rate of change of one unit to the other. Okay? In fact, if r is my radius, and I know it's changing at 1 foot per second, how might I write that as an equation? Exactly. dr dt, which is the rate of change of the radius with respect to time, is just 1. Okay? So that's what that information right there tells me. So that is equal to 1. Okay? The next thing it tells me, it asks me, is when r equals 4, what is, and it says, what is the rate of the total area of the disturbed water? How fast is it changing? What is the rate of change for the total area? So what variable would you use to represent area? A, right? So it's asking for what is the rate of change of A with respect to time. So first of all, what is the equation? What's the equation that represents the variables A and R together? I don't mean the one involving the derivative. I mean, is there an equation that describes the object that we're looking at? We're looking at the area of the outer circle, so what is it? A is equal to pi r squared. Okay, what have we been given? We've been given the radius. I'll write that down. R is 4, right? And what else do we know? So dr dt is constant. It's always 1. Okay, what do we want to find? Not just area. Exactly. Rate of change of area. In general, all these are going to be done then a similar way. We're going to take the equation and take the derivative of both sides with respect to t. So the derivative of A with respect to t? Exactly. What do we have on the right-hand side? The pi hangs out because it's a constant. Derivative of r squared is 2r times dr dt. Now we know what we're given, right? Plug in our givens. 2 pi. We were straight out given that it's 4. And dr dt is 1. So the answer is 8 pi. By the way, what were our units? Did they tell us? Inches, feet. Oh, feet per second. So this would be, what is the unit then for area? If the length unit is a foot, square feet, or foot squared, say it however you want to, per, and then unit time was second. So there you go. Unit of A per unit of T. Now, the hard parts of these can come up in different places. Sometimes it's difficult to go back and remember your formulas that relate these things. I think in general, most of the problems I give you, that's not going to be the hardest part. We should be able to look it up. There are some geometry formulas in your appendix and in the back of your book, so you can look to those for some assistance there. Sometimes, like this problem, everything's nice and easy. They give you all the things that you need. That is, when you get to this formula right here, actually, I should say this formula right here. Notice there are how many unknowns in that equation? There's the dA dt, there's the r, and the dr dt, right? They gave us 2 of them, 2 unknowns, so we had only 1 unknown left. 1 equation, 1 unknown, we solve it. Okay? Now, sometimes they may give you only part of that information, and you have to go back and use either this equation or other information in the problem to figure out the rest of the variables that you need to plug in. Okay? We'll see that in an example coming up. All right? Any questions about that? Equation, you find what you're given, and then you calculate the thing you're looking for, the dA dt in this case, by using implicit differentiation. Okay. Let's do another one. Well, there's questions on that one. Let's do the inflating balloon. While we're thinking of nice round objects like ripples in a pond, now we're doing a sphere. So we're moving up into 3 dimensions. This is on page 142 of your text, and it says air is being pumped into a spherical balloon. They even got some pictures there for you. We know that it's being pumped in at a rate of 4.5 cubic feet per minute. We want to find the rate of change when the radius is 2 feet. So you've got your balloon. Actually, you know what? I don't know why I don't use something like this awesome little doohickey. Isn't that a nice round circle that I can't do on the board, but I can do now on my screen? There's my balloon. And by the way, there's a little trick that I will always use, just so you know what I'm doing. To make something look three-dimensional, it needs a glare, right? It needs some shadowing. So instead of spending the time actually shadowing it, I'm going to put this on there. There's the glare. Doesn't that look 3D now? It's like it's coming right at you. I don't know where. I guess I learned that from my own calculus professor. Dr. Alms used to do that all the time. So you knew he was drawing something in 3D. Like he would draw a surface up on the board, right? And first it looks like just a weird shaped thing, and then he'd do this. You'd go, oh, that's the three-dimensional surface. So now we know. That's what's going on. So this is the balloon that's coming out at you. We are told that its rate of change of its... well, air's being pumped into it. What are the units of the thing that's changing in the paper? It's on the problem. It says 4.5 cubic feet, which is a measurement of what? What is cubic feet? Volume. Per minute. Okay? So that was d volume dt. What do we want to, well, what are we given? That's what we were given. Let's not write that down yet. What else do we know? We want to know, find the rate of change of the radius when the radius is 2 feet. So first of all, what's the equation that relates the information or the variables in this problem? The variables are volume and radius. So what's the volume of a sphere? Close. There is a 4, there is a pi, and there is an r cubed. But there's something else. 4/3 pi r cubed. I guess its surface area is 4 pi r squared. So that's the one that has just the 4 in it. Okay. What are we given? So R is 2. What else are we given? Not our volume specifically, but our change in volume, our rate of change in volume. It is important to make that distinction. Those are two different quantities. It's the difference between a function and its derivative. All right, so what are we asked to find? Do what? So d r dt. So take derivative of both sides of v equals 4/3 pi r cubed. Take the derivative of that with respect to t, d dt. So that gives me dv dt. You guys should be able to do this flying colors right now. Another easy one. But hopefully that's what you get. dv dt is equal to 4 pi r squared dr dt. Which, by the way, is kind of interesting. I don't know if you noticed that. We mentioned it before. I said it offhand that the 4 pi r squared happens to be that surface area for a sphere. Do you notice now there is, or at least appears to be, a connection between the volume and the surface area, right? It's like they are, in a sense, derivatives of each other. Do you notice that actually happens with circles as well? A is equal to pi r squared. What's the derivative of that? 2 pi r, which happens to be the circumference, are related as derivatives of each other, or one is the derivative of the other. Hold on to that. We'll think about that much later. All right. So dv dt, piece of cake, just plug it in, right? 4 pi. Actually, what do we know? We don't know dr dt. That's what we're trying to find. So we know dv dt happens to be 4.5 equals 4 pi, and r is 2, and dr dt. Notice how the information can be given so that it's not always the left-hand side that we need to know, right? Like last time we wanted to know dA dt. Now we want to know dr dt when we know what dv dt happens to be. But that's still just an algebra problem. You get 4.5 is equal to 16 pi dr dt, which would mean dr dt is 4.5 over 16 pi. Anybody got a calculator that can plug that in real quick for me? I guess we could cheat. This 0.088?
0.88.
You sure? I don't like that answer. Yeah, that might ought to do it. Divided by 16, and then divided by pi. Where's pi? So rounded would be 0.09.
Yeah.
And what are the units going to be? What are the units of r? Feet. What are the units of t? So the radius is changing at 0.09 feet per minute. Yes?
On the dv dt equals 4 pi r squared.
Right here?
How come that's not huge?
Well, it's when I took the derivative of what's inside, right? I'm taking the derivative of this. The 4/3 hangs out, the pi hangs out, and then you take the derivative of r cubed, which is 3r squared times dr dt. So it's that power rule. When you bring the 3 out front, drop that power by 1, it becomes a square, and then I cancel these 3's to get 4 pi r squared. Yes, sir?
When we're doing homework, what do you want us to round to?
I'm not going to be picky. The general rule of thumb is usually to do one more decimal place of accuracy than the units in the problem. So the units in the problem went to 4.5, right? So I went one more decimal place than that. Although a better rule is to do significant digits, which I didn't obey here. Significant digits means I've got 2 significant digits on my volume, so I should probably have 2 significant digits here, which would be a 0.088 or something like that. So because of there are opinions that differ on that. If you're working for NASA and you're tracking a probe that's flying from here to Mars, you probably want to go the more decimal places you can, right?
Yeah.
But if you're working for Dr. Franklin grading, then it's not. Yeah, I don't have any qualms about saying that. That's my least favorite part of this job. All right, easy enough. All right, let's turn it up a notch just a little bit here. I tell you what, let's skip example. No, actually, we need to do example 4 because there's one like it in your homework. I better go ahead and do that one. So example 4 in your text, this is on page 143. This is the speed of an airplane tracked by radar. Page 143. An airplane is flying on a flight path that will take it directly over a radar tracking station. And they give you a figure there. We'll draw a picture of it in just a moment. If S is decreasing at a rate of 400 miles per hour, when S is 10, what is the speed of the plane? Okay, so the picture looks like this. You've got the radar dish down here, right? It's pointed up at the plane up here. That looks like a plane, doesn't it? Not so bad. And the height of the plane, above that distance of the radar. So what information do we know about this, say that right triangle right there? How high is the plane? 6 miles. What are they calling this? They call that X. Now, X is how far away this thing is, and it's traveling along that path X. So the velocity of this plane is going to be what quantity in this problem? The velocity. How would I write the velocity in mathematical notation? If X is this distance that it is away from the radar, then how do I write the velocity of that plane, other than just writing V? No. It's not traveling along this way. We're not doing anything about the relationship between these two. Whether it's here or here or here, I'd still use the same symbol to represent velocity. Kinda. I mean, average velocity is change in x over change in time, right? But I'm talking about instantaneous velocity. Remember when we talked about this? It's the change in position over time. And since it's traveling along this path, then I suggest that it's traveling along that distance x, that the change in x over time is going to be the velocity of that plane. Yeah. So dx dt is the velocity of the plane. I'm just throwing that in there for extra information. And they called this distance here, straight line distance, as s. Okay? They tell us that s is decreasing at a rate of 400 miles per hour when s is equal to 10. Okay? And so they want us to know what is dx dt when s is equal to 10. So notice we're given, I'm starting this out of order, but that's, as long as you get the three components, you got to know what the equation is, you got to know what you're given, you got to know what you're trying to find. What are we given in this case? S equals 10, and what does this tell us? What is negative 400? Exactly. It is how fast s is changing, and why is there a negative there? Yeah, it's getting closer, but the key word here is decreasing. Decreasing tells us that that derivative is going to be negative. When a derivative is negative, that's when it's decreasing, or vice versa. When we say it's decreasing, the derivative means it's going to be negative. Okay? All right, what do we have to find? Right, does that make sense? You're asked to find the derivative, meaning actually you're asked to find the velocity. You got to be able to make sure you understand that that means the rate of change of x with respect to time, or write it as dx dt. Now, what's the equation in this problem? What equation do you have that relates, well, what's our two variables? We have s and x. Yeah, it's a right triangle. So x squared plus 36 equals s squared. Just a geometry formula to do that. All right, so let's now take d dt of both sides. d dt of x squared plus 36 equals d dt of s squared. What's on the left? 2x times dx dt. Remember, we're taking with respect to t, so you got to use the chain rule. On the right, okay. Well, first thing I notice just right away to make life simple, I can cancel those 2's out, right? Divide both sides by 2. So what you actually have is x dx dt equals s ds dt. How many unknowns are in that? I mean, ignoring what we're given for right now, just how many different things would we have to plug in? We have x, we have dx dt, we have s and ds dt, right? So we need to have 3 of those things. So what do we know? We know s is equal to 10. What over here? Well, we're trying to find dx dt, so we know we're not given that. What about the x? Did they ever tell us what the x is?
X equals square root.
Yep. So in this case, we need to find the x, right, that goes with this. Meaning, we're given this was 6 and this was 10, right? So we can either do it geometrically or we can just do it right here from this formula, right? So finding x, we just plug in x squared plus 36 equals 10 squared, which gives me x squared is plus 36 equals 100. So x squared is equal to 64. So x is 8. So that's where the occasion might arise where you're not given one of the values, you have to find it. You have to use the information given in the problem to figure it out. Now we've got only one unknown here. If I divide both sides by 8, I'll have dx dt is equal to, 8 goes into 450 times, so negative 500. So if you'll notice, by the way, the question is, what is the speed of the plane? Negative 500 is the velocity. What is the speed? 500 miles per hour. Because it's always the absolute value of the velocity. All right, let me scan. All right, I think you're in pretty good shape there. There's a couple more examples in the book that you can refer to, and I encourage you to read through them if you're having some trouble with these problems, just so you can see some more examples being done. But that is actually enough for, I think, you to have a pretty good handle and a good reference tool as you start to work on your homework for this section. All right, now before we dismiss class, I need to make an announcement because it's time for your test. Aren't you excited? I'm going to go ahead and stop this video because you don't need all this information on the video. Stop.